Suppose, in case we have to find the center of mass for a continuous mass distribution system, we have to select a point mass in the continuous mass body. Then xCm can be obtained as integration x dm upon integration dm, where x remains the position of the chosen element as point mass with respect to reference point. Similarly, yCm is equal to integration y dm upon integration dm, and zCm equal to integration j dm upon integration dm. In these equations, x, y, z are the position of center of mass of the chosen element with respect to reference point. Now, if we are interested in finding out center of mass for two point particle system M1 and M2 as shown in figure, separated by a distance r. Suppose center of mass is located at a distance x from M1 and r minus x from M2. About center of mass, since moment of masses gets balanced, so we can write M1x equal to M2 r minus x. After solving this equation, we will get x equal to M2r upon M1 plus M2 and r minus x equal to M1r upon M1 plus M2. Now, since position vector of center of mass is M1 R1 vector plus M2 R2 vector plus dot dot Mn Rn vector divided by total M. If we differentiate equation of position vector with time, we will get velocity of center of mass, and again if we differentiate velocity of center of mass with respect to time, we will get acceleration of center of mass. So what we get for VCM? VCM vector equal to M1 V1 vector plus M2 V2 vector plus dot dot plus Mn Vn vector divided by total M, where V1, V2, V3 dot dot Vn are the velocities of individual particles comprising the system, and VCM is the velocity of center of mass. Once again, if we differentiate equation of velocity of center of mass, we will get acceleration of center of mass as acceleration of center of mass equal to M1 A1 vector plus M2 A2 vector plus dot dot Mn An vector divided by total M. So, acceleration of center of mass can be written as summation Mi Ai ranging from I equal to 1 to n divided by summation Mi ranging from I equal to 1 to n. Total mass when multiplied with acceleration of center of mass gives us force acting on center of mass. So FCM equal to M into ACM, that is equal to M1 A1 vector plus M2 A2 vector plus dot dot Mn An vector. According to Newton's second law of motion, external force acting on a body remains equal to rate of change of linear momentum with respect to time. So FCM can be written as d by dt PCM. If FCM is 0, what it indicates? If FCM is 0, means ACM is 0, means VCM is constant. When velocity of center of mass is constant, then the system, that is center of mass, will remain in translatory equilibrium. When velocity of center of mass remains constant, dear student, remember very well, it does not mean that the velocity of individual particles comprising the system also remains constant. They may get changed. Suppose, for example, there is a compartment kept in a moving train which is accelerating, then the compartment will be at rest with respect to train. If the gas is being filled up, if the gas is existing inside the compartment, then velocity of individual particles inside the compartment may get changed, but velocity of center of mass will remain constant. in the compartment frame, velocity of center of mass will be equal to m1 v1 vector plus m2 v2 vector plus dot dot mn vn vector divided by total m. Since compartment is at rest in the frame of train, so acceleration of center of mass of compartment is 0, and here velocity of center of mass is also 0. Velocity of center of mass of compartment filled up with gas is 0. It does not mean that the velocities of individual gas particles existing in the compartment is also 0.